All right, here is a practice problem that we didn't have time to do in class on Friday. So I wanted to walk through it with you guys. So this is calculate the molar solubility of magnesium hydroxide in pure water. So that's the first part. And then in a solution of 0.0862 magnesium chloride, that's the second part. I've given you a KSP, so that is your equilibrium constant for solubility for magnesium hydroxide. And then, so the first question is, what is molar solubility, right? So we need to know kind of what this means in order to answer this question. So really just this refers to the concentration of magnesium 2 plus and OH minus that's formed from dissolving magnesium hydroxide. So we just want to know those two concentrations. So it's very similar to a weak acid and the percent dissociation, right? We want to know what are those concentrations. So we approach it the same way, just like an ice table. I'm going to take some of this away and I'm going to add these products, and I'm going to add X to magnesium 2 plus, and I'm going to add 2X to hydroxide because there's a coefficient of 2. And then I'm going to end up with X and 2X, and I do not include this in my equilibrium expression because it's a solid, right? So then I have a KSP of 1.8 times 10 to the negative 11th, and that equals the concentration of magnesium 2 plus times the concentration of OH minus squared, since there's a 2 in front. And I plug in X and 2X for my equilibrium expression, solve for X. So if when I distribute X, I have 4X cubed. And when I solve for X, I get 1.7 times 10 to the negative 4th molar. So then this describes the concentration of magnesium 2 plus, and then it also describes 2 times X, which is the concentration of OH minus, which ends up being 3.4 times 10 to the negative 4th molar. So in pure water, I can tell how much of that has dissociated into magnesium 2 plus and OH minus. Now the second part asks, what is the molar solubility in a solution of 0.0862 magnesium chloride? And magnesium chloride completely dissolves, so we have this reaction taking place here. Magnesium chloride goes to magnesium 2 plus and 2Cl minus. So this concentration is going to be the same. As you can see, I have a straight arrow to the right. There's no equilibrium here. 0.0826 moles per liter of magnesium 2 plus is what I will form. And so now I want to know, with my magnesium hydroxide solution, how is this going to change the equilibrium concentrations? So what I'm going to do is I'm going to take my equilibrium expression here, and instead of starting with X for magnesium 2 plus, I already know that I had dissociated some amount, a very small amount, to begin with. And so if I add 0.0862, that's going to be a pretty large difference in having that concentration there. So I'm going to add these two together because essentially I'm going to say I already have that amount of Mg2 plus in solution. But as you can see, it doesn't make a huge difference in that overall concentration. So I still want to know how much hydroxide will actually be left in the solution if we have this initial magnesium 2 plus of 0.0862 molar. Now, think about this in terms of Le Chatelier's principle. If I start with more magnesium 2 plus, which way will the equilibrium shift? It will shift to the left. And when that shifts to the left, what happens here is magnesium 2 plus combines with OH minus to make more solid. So precipitation occurs. So I want to know, well, if some of this has to combine with this to make more of this based on starting with 0.0862 molar, I want to know how much is actually left over. So I'm still going to be solving for the concentration of OH minus in solution. So I can set this equal to my KSP here and solve for X again. So I get that X is 7.2 times 10 to the negative 6th. And now I want to solve that for OH concentration, so I have to multiply that by 2, and I end up getting an OH concentration of 1.4 times 10 to the negative fifth. So the question is, does this make sense that the number is smaller when I start with some amount of magnesium chloride or magnesium 2 plus in solution, right? Because originally I had an OH concentration of 3.4 times 10 to the negative fourth, and now I have a concentration of 1.4 times 10 to the negative fifth. So yes, it does make sense that it's smaller because my equilibrium has shifted to the left based on having more magnesium 2 plus already in solution. This is the same idea as the common ion effect that we talked about. The common ion effect, or adding a common ion, will shift the equilibrium in your solution. So yeah, that's it. Let me know if you have any questions.